I think it would be worth giving a small example or two of what overfitting is, so you have some sense of what we're trying to avoid as we go forward. So I'm just going to make up a couple of quick examples. Suppose we're interested in the relationship between class year and number of statistics courses completed, right? So we might have a data set that looks like this. Here's class year, and here is number of stat courses. Okay, and let's see, maybe I have a senior who's taken 2 stat courses, and I have a junior who's taken 1 stat course, and maybe I have also my data set a first year who somehow took 5 stat courses. Right? Suppose that happened. That's sort of possible. Suppose that happens. Okay. Now, if I want to describe a pattern in this data set, well, certainly I could estimate the mean. If these 3 people are representative of all Wellesley students, I could have a model that looks like this. I could say the mean number of stat courses is equal to just some number beta 0 and not include any sort of predictor, such as class year, and I could estimate beta 0 to be the mean of these 3 numbers, right? And that would be one possible model. That's the equal means model. Or I could try to do it based on class year. I could have my model say, hey, I want to have a different prediction depending on your class year. Okay, so I might say the mean number of stat courses given your class year is going to be equal to, I don't know, well, in this data set, there's no sophomores. So let's say there's 3 possible class years. And when you have a categorical variable with 3 levels, you pick one as a baseline and make 2 indicators. So I might do beta 0 plus beta 1 times whether you're a junior plus beta 2 times whether you're a senior. And so if you're neither a junior or a senior, you might be a first year. Okay. So thinking about this equation, the way we've thought about these equations previously, let's see, to estimate beta 0, well, beta 0 is the mean number of stat courses when you're not a junior or not a senior, therefore you're a freshman, first year. And based on this data set, there's only 1 first year and her mean was a 5, right? And I could do the other one similarly. Beta 1 is going to be the change in number of stat courses when you go from a first year to a junior. But looking at this data set, I have to go from 5 to 1, so I need a negative 4 here. And for beta hat 2, right? Let's see, that's the number of difference in number of stat courses between a first year and a senior. So I need to go from 5 to 2, so it's going to be a negative 3. Okay, so all I did was estimate those parameters the way we have been doing previously. What's the problem? Well, if I only have 3 data points, if n is actually equal to 3, and I fit this model, this is the model I'm going to get. But is this a useful model, right? If somebody new walks in and that person is a first year, and I try to use this model to come up with a prediction of the number of stat courses they've taken, I'm going to predict 5, because the only first year in my data set happened to be this unusual person who took 5 courses. But have most first years taken 5 stat courses? Definitely not, right? If I try to interpret these coefficients, if I try to say, okay, let's interpret beta 2. Beta 2 is the difference in average number of stat courses that a senior has taken over a first year. If I use this data set that only had 3 people in it, my best guess at the difference between the number of stat courses that a senior has taken versus the first year is negative 3, right? But it's not actually true that seniors have on average taken 3 fewer stat courses than first years. That's just because my data set is really small, right? My data set is so small that my coefficient estimates are reflecting the particular individuals in the data set, but they're not generalizable. Using this second model here, I can neither make a prediction accurately for any particular person who's not in this data set or interpret these coefficients. So why did that happen? Because the number of terms in this model, beta 0, beta 1, beta 2, the number of parameters is too big for the size of the data set. If your data set really only has 3 people in it, you're better off with a model like this where you don't even try to use a model that has so many parameters. Here's another example. suppose that I have a continuous predictor. So maybe this is number of math courses taken in high school, and then number of stat courses that a senior, number of stat courses a senior has taken. Okay. So I don't know, I'm gonna make this up. I don't know how many math courses you take in high school, probably not more than like 6 or something, right? So suppose I gather some data, and it looks like this. Okay. Now the way I drew that, I tried to draw it so running a linear regression would not be ridiculous, right? And that yellow line comes from a model that looks like this, like the mean number of stat courses is equal to some intercept plus some slope times the number of high school math courses, something like that, right? Okay, intercept and slope. And that seems like it'll be okay. Like if this were my model and I get a new person in the data set and told me they took 4 math courses in high school, like I'm pretty comfortable with that number being my prediction for the number of stat courses they might take by senior year at Wellesley. That seems okay to me. But what if I added additional terms to my model? What if my model was everything I've written here plus beta 2 times number of math courses squared? Now I'm going to make something a little bit more like a parabola, right? Okay. So I'm going to update my prediction to this. Is that a better prediction? Maybe, right? What if I keep going? What if I add plus beta 3 times number of math courses cubed? Well, now, I guess I should have done that in a different color. I'll just underline it in green. Now I'm going to have something with a little bit of a curve to it, like this, right? If I keep on adding terms, I'm going to be drawing models that look closer and closer to these dots, but I actually don't want a model. Like the perfect model is not the one that exactly connects all these dots, right? That's not the perfect model. The perfect model is the one that averages together these dots to give my best guess. And in this case, I actually think the yellow line is more likely to lead to good predictions than this red thing I drew that looks a little bit more like a spline. Again, the more polynomial terms I add to this model, so math courses squared, math courses cubed, et cetera, the more that the curve that I'm drawing will not look like a line or even a parabola, but look like a curve that goes through the individual data points. So the residuals will get smaller because the fitted values will be right on the data points, but that model is not going to be generalizable to future values because there's no particular reason that the next person in the data set who's taken 4 math courses in high school should have exactly this number of stat courses at Wellesley. Rather, I'll draw it again, this yellow line here that averages across the data points they actually observed is probably more accurate predictor. And I will show you some code that does something similar as we go forward. So both these are examples of overfitting. Again, the previous slide, I'm saying, hey, if the number of data points is too small relative to the number of parameters in your model, then your predictions are exactly equal to your past values. They don't generalize at all. And you can't interpret the coefficients because, again, they're just exactly about your past data set, which is too small for the number of predictors. And I'm saying the same thing here. If you have too many parameters in your model, too many terms that require betas, then you end up with a model that fits the data very well, but is not useful for generalizing to future values.